All right, the last few things we're going to look at here are ionization energy, reactivity, and electronegativity. So ionization energy is the amount of energy required to remove an electron from an atom, and that was from the last worksheet you had to do. Okay, using this concept, an element with a large ionization energy does not lose an electron easily. That means you have to take lots of energy to do something. So if it's big ionization energy, it means it takes lots of energy to do it. All right. If we look at our periodic table, we're going to look in a second, with the pictures of the ionization energy, which group of our elements is going to lose electrons the easiest? And you'll see that it is metals. Okay. So if I change this, again, a little gear in the upper right, and I'm going to change this to ionization energy. All right, we see this really red in the upper right corner. Okay, it's really red up here with like fluorine especially. Notice how if we see how it says ionization energy of 10 and up. So we see the right side for the most part has really high ionization energy, okay? And the ones to the left are a lot lower. Now you see there's a little red pockets in the middle, okay? Transition metals, or D blocks, can be kind of crazy. They don't always go with what they should. But for the most part, our trend kind of goes to the right, or the really high ionization energies are definitely at the right of the table, okay? So we're going to think about our atomic radius trend and the fact that it takes a lot more energy to take any electron from any one of these guys here on the right-hand side of the periodic table. Well, if we think back to our trend, okay, we also have a really small radius over there. So if I have a really small radius on the right side of my table, it's actually harder to take an electron, which should make sense because if my electrons are closer to my nucleus, it's going to be much harder to take this electron than for something like francium, which is over here in the lower left, where its electrons are really far away from it. Well, it's going to be easier to take something from somebody if they're holding it way far away from their body versus if they're holding it really close to their body. So ionization energy and radius trend actually go very well together. And it goes for both of these next two questions where we talk about going across the period left to right for the periods and also down the groups top to bottom. Works the same way. The elements here at the bottom of my periodic table are very large, so they're very small ionization energies. So ionization energies increase as you go to the top and to the right on your screen there, okay? And another way to look at this is actually with those same kind of graphs that I showed you earlier, okay? And with those graphs, that was atomic radius, okay? This is ionization energy. Notice how this one decreases as I go from the left to the right there. This one increases as I go from the left to the right, which would make sense because this is the first period. So there's hydrogen, here's helium. I go to lithium to neon, and notice it increases. Okay, as I go from sodium to argon, it's going to be increasing. Okay, so they're the exact flipped. Okay, notice how one's increasing, the other is decreasing. They're the exact opposite. So these work very well hand in hand together. So I'll give you a second here, oops, actually, and I will let you copy down what I just wrote, or what I just said, which is what I have written down there, which will be for those two, this one here and that one there. All right, so now we're going to talk about a term that deals with second ionization energies, and this is going to be more in the next video. But we're just going to mention it here. A second ionization energy would mean that you would take a second electron. A third ionization energy means that it would be the energy to take a third electron. Fourth ionization energy, the energy to take a fourth electron, and so on and so forth. So second just mean that second electron, or the energy to take the second, then the third, then the fourth, and so forth. Okay, so the last things we're going to look at here are reactivity and electronegativity. Okay, reactivity works with ionization energy. Okay, if we talk about how reactive an element is, reactivity deals with how easily it takes, or how easily it is for an element to form a bond. Okay, metals love to lose electrons. All right, metals have really, really low ionization energies. Okay, for the most part, metals, remember, are that left side of that table. Notice how this one on the left is very yellow. My nonmetals over here are very red. Okay, so they are very high ionization energies. So the most reactive metals are actually in the lower left because those are actually the lowest ionization energies when you talk about metals. All right, now when you deal with nonmetals, ionization energy doesn't work quite as well. Okay, you're dealing more with size. Okay, reactivity increases as you go up to the upper right. Okay, when you're moving to the upper right, those actually have to gain less electrons. Okay, to be a noble gas, and we'll talk about here that basically every element wants to be a noble gas. You're dealing with those. Okay, and the energy to do that. And that's going to be a little bit more in the next video where we talk about that. But the lower left-hand side of your periodic table also are the larger in size. So they're kind of harder to interact with one another, which means that you're dealing with something that's not really easily going to bond with something else. Okay, so upper right, it's kind of backwards. Upper right for the nonmetals and kind of lower left there for the metals. Okay. Now, for the last thing we're going to deal with here, which is electronegativity. Okay, electronegativity, we're going to just kind of mention here, talk about what it is, and then we're going to leave it a lot more for some later chapters. Okay, when atoms bond, okay, they share, lose, or gain electrons. So that's going to be a big thing in the next few chapters. We're dealing with electrons, okay? Electronegativity measures how attracted electrons are in a bond. So I'm talking about this element to this element. They have electrons in the middle that they share. They don't always share them nicely or very equally. Okay, the most electronegative element is actually fluorine. All right, and so if I look at a bond between, say, Si and Cl, Cl is actually more electronegative. I'm going to look at the chart here. I'm going to show this to you, and that means that the electrons between silicon and chlorine spend more time near chlorine. So I kind of have these two dots there being my electrons that they're going to share. Okay, and they're just going to hang out more around chlorine, basically. So we're dealing not with taking an electron from something, but I got these two things bonded, and they're not kind of sharing nicely, or the tug of war isn't kind of going very well for one of the atoms, okay, or one of the elements. So when we look at electronegativity, okay, so if I change this to electronegativity, which should let me do this here, we'll see, you will see that fluorine is the highest number. We see how fluorine there is really, really purple. Okay, fluorine actually has a value of 4 for electronegativities. And for the most part, when you get further away from fluorine, it gets lower. Now, NO and Cl are kind of the next ones that are really electronegative, and then it kind of just gets smaller as you get lower. And I'll show that to you in the form of a picture, those graphs again as well. So if I looked at electronegativity, okay, you see the biggest one here is right before atomic number 10, which would be fluorine, okay? Or neon would be 10, fluorine would be 9. So this is fluorine right here. And so it kind of increases across the period to fluorine. And then it drops back down for the next period, increases across to fluorine, drops back down, increases across to fluorine. So you're dealing with, basically as you get closer to fluorine, it gets more, okay? You can read the groups on these things too as well. I don't know if I said that earlier. But I can also see groups in these if you pick out which elements are which. So you can see, like for atomic radius, lithium to sodium to the next one that in the group, okay, it goes up. So my atomic radius increases as you go down a group because lithium, sodium, and potassium are all first in those groups. Same thing goes for ionization energy. Helium to neon to argon, those are all in the same group, and they get steadily lower, which is what ionization energy does. That's an atomic mass one. Okay, that one's easy. Your atomic number gets bigger, your mass gets bigger for the most part. And again, there's 2 little changes there, but for the most part it does. And that is the end of this series of videos.